Our next speaker is Yury Gorbachev from Itseez, and he's going to be talking specifically about OpenCV for embedded systems, lessons learned. Although, I guess actually the British have a thing that they say it's not actually a lesson learned, it's a lesson identified, and next time we'll find out if we learned it or not. So, do you want to use we use the podium mic? Yeah.
Okay. Yeah. So amazingly, you ask a question, you get presentation out of it. So half an hour answer. Thanks everyone for joining, and let's first look at what OpenCV, to those who maybe forgot that or something. First of all, we as Itseez are the company who maintains OpenCV for more than 6 years or even more. Customer are using OpenCV, and we implement products with use of OpenCV. So basically, we know both sides of the game when it comes to OpenCV. So we are using it actively, and we are maintaining it, and not accepting patches. This is also to us. So the library runs on desktop operating systems as well as mobile operating systems already out of the box. So that's important aspect when it comes to embedded, that we actually support platforms that run on embedded systems, although it's a little bit like a user-oriented or embedded systems. And the library currently is using purely C++, so we abandon C language, and in third release we are not going to, most likely we are not going to allow C interface anymore, because it's getting very hard to maintain it. So let's first look at what desktops are and why it is good to work on a desktops, although we are talking about embedded right now, but just to compare. So OpenCV on desktops provides pretty much everything for you to create applications. So you can grab frames from camera, from video, and more importantly, you can output results of your processing, intermediate steps of your processing on the screen in the UI and different windows, separate windows. Basically, you can create application just using OpenCV. Everything is there. You can have buttons, simple buttons, but you can have them. So everything is available to you. Then on the PC, on the desktop PCs, you get quite decent performance out of the box. So it's not only the CPUs are powerful, scalably powerful, or just like GPUs or everything, but OpenCV is quite good optimized for desktops. That's mainly because it was initially running on the desktops. So you get very good performance, and some of the algorithms, despite the fact that they are probably inefficient or anything, they can be running in real time out of the box without without the need for optimization. Even though if you might be in a need to optimize algorithms, then you can use interfaces that are pretty stable. So TBB for multi-cores, SIMD, OpenCL, CUDA, everything is working on a desktop for quite some time. People are quite frequently using it, so you get everything there. So, but as soon as you go for embedded, everything changing dramatically. So you're not able to grab frames in a quite easy manner. To be honest, I mean, OpenCV doesn't allow you to grab frames on most of the embedded platforms because of the specific interfaces that they use on those embedded platforms. On most of the platforms, you are not able to read video files with OpenCV, and you have to use some external libraries or something like that, simply because we are not, as an OpenCV maintainer, we were not investing much into making everything running on most of the embedded platforms. Then you get performance degradation right when you go to embedded platform. Your algorithms are starting to suffer from thermal protection on a mobile platform, from power saving and so forth. So things are getting incredibly complicated when you do that. And if you want to apply optimization techniques, then it's also different from system to system, from SoC to SoC. So certain platforms can provide you OpenCL, certain platforms provide you DSP, but it's different from platform to platform. So things are quite complicated there. Luckily, OpenCV as such and algorithms that are based on OpenCV can be quite easily migrated from platform to platform and migrated from desktop to embedded because OpenCV has only one strict dependency, is a CMake to make the library. As soon as your platform supports C++, most of the processing modules are able to migrate to this particular platform. And it's not only that you can recompile your algorithms or recompile OpenCV for this particular platform. OpenCV now contains accuracy tests. Accuracy tests allow you to verify that thing that you recompiled actually performs as expected. So as soon as you start your porting efforts for a new platform that doesn't support it by OpenCV, for example, you can run accuracy tests and you can verify that the compiler is generating correct code, and you can verify that library is compiled correctly and produces expected results. To tell you more, some of our customers, silicon vendors and just platform providers, use this functionality to verify how good this new environment behaves. So if they replace one compiler with another, like migrate between GCC versions and so forth, they can use OpenCV accuracy tests just to verify that everything is compiled as expected. So this is a very powerful tool, not only to verify that OpenCV migrated, but also for as a hint if you are like a platform provider. So given all this, our recommendation when it comes to OpenCV and developing things for embedded platform is to actually use the desktop for development. Believe it or not, but we recommend to do that first and then go to embedded platform. So using desktop allows you to develop, to concentrate on your algorithm as such. So you actually see the internals, you actually see what's happening within your algorithm by use of debug output, by use of output of intermediate steps and things like that. You can get that on the desktop in a very easy manner, as I have described before. And this all allows you to concentrate on the algorithm, not only on debugging it, but also on like the particular specific aspects of your algorithm. So you can look at what intermediate steps producing, you can look, maybe this is not satisfying you and so forth. That possibility doesn't present when you work on embedded platforms most of the times. So then, as soon as you think that your algorithm is stable, you wrap that with the regression tests and migrate to the target platform. And regression tests will allow you to verify that your algorithm is still working okay. Most of the OpenCV modules, as I mentioned, will be verified by accuracy tests, but then your algorithm, you need to verify that as well. Of course, you will see that performance is becoming an issue after the migration, so you have to do a profiling step. So we recommend to wrap certain parts of the algorithm with the performance checks, performance measurements, so that you could see which particular parts of your algorithm consuming more. Then you do bottleneck optimization. That's clearly because you have identified them, and fine-tuning. And it seems that you are ready to go. But we will talk about things that you will see as soon as you start migrating. And probably you should know that beforehand, before you actually start implementing everything, before you're thinking of going for embedded application. So hardware is also, hardware always an issue for vision systems. So as soon as you start implementing something significant, you will see performance problems. There is a common mistake when people think that, okay, I have a 8-core CPU, now I will get everything fast as soon as possible. That's not true, because computer vision tasks are very memory hungry and very much depending on memory bandwidth. So it can happen that you have 8 cores, but most of them will be idling because your function that is executing is pumping a lot of memory. Then tasks, the applications that you implement for mobile platforms, like some user-specific things, I don't know, like playing with background subtraction and so forth, have another difficulty, is that mobile platforms are usually unpredictable. The systems start to protect themselves from overheating and from draining much power, and your algorithm simply doesn't know when that happens. There is no API or anything like that that allows you to say that you are consuming too much, or you are overheating, so you should start skipping frames or something like that. That simply doesn't present for the moment, and it's very hard to predict when that happens. So if you could, probably you could start skipping second frame or something like that, but that doesn't present. So unstable FPS that you will get will impact your algorithm. Probably if you develop that on a desktop, you will not see that. However, on the embedded system, unstable FPS will impact the algorithm immediately. So you will start probably losing tracking of object, or your famous structure from motion algorithm will stop working, and so forth. So, but a good thing is that you can emulate this on a desktop again, because you can just start skipping frames from video or from camera, and again you can overcome that issue, overcome that tuning issue on a desktop. And if your project involves hardware selection, this is also not easy, because first of all, you are not able to predict what performance you will get on the system. And this is mainly also related to the fact that there is no vision benchmark at the moment that tells you that certain particular SoC will behave in a good manner or bad manner. You don't know that. Integer benchmarks doesn't show the full picture, as well as float benchmarks. So there should be some benchmark that you probably could execute, but there is no. So after the migrating step, basically after the initial migrating step, what you will see immediately that algorithm that was working super fast doesn't work that anymore on the embedded platform, and there are two reasons basically. First is that SoCs doesn't work very fast, but also OpenCV is not optimized for mobile platforms or ARM-based platforms, as well as to the same extent as for x86. So there are numbers that are given here. There is outstanding number of Neon optimized functions for 2.4, OpenCV 2.4, which is 5. And SSE optimized functions at the same time is 150. So there is a pretty good chance that you have a difference between x86 and ARM-based, just because function is not optimized. So some optimization can help. We have a couple of hints for optimization on the algorithm. First of all, look at the algorithm optimization. Some people think that we had the algorithm, so we had to go and optimize that with Neon, and it's not working fast as we expected. So what to do? Everything is lost and stuff like that. But first of all, you have to look at the algorithm. Probably you are calculating optical flow on RGB images, or like working with full HD images when it's not needed, and so forth. So just probably look at the algorithm where you can optimize, where you can reduce processing, like reduce areas for search, reduce tracking areas, use grayscale images, That only you know, but you should do that prior than looking at the actual optimization with Neon. If you are able to influence hardware, then try to execute your algorithm on multiple development kits if that's possible, because this is really showing you the performance of your application. Some hardware vendors deliver OpenCV, which is basically with the same interface but optimized within. So NVIDIA and TI are known to us deliver that. Although you're not able to use that on the whole set of SoCs, probably like only on NVIDIA or TI. But if your target platform is that, then you have an optimized solution there. Finally, you can go and optimize with Neon or other available means yourself, but you have to identify bottlenecks first and then go that. So just to show what can be achieved. So as you can see, some functions can be optimized 50 times by using Neon. That's a pretty good number. But some functions cannot be, and you can get only 5 or something. So it would be premature to say that if you have a Neon function, then you can go and optimize that 50 times. But however, you can expect in some cases pretty good optimization. One hint that I can also give you is that ARM v8 has very good scalar performance, so probably you will not need Neon optimization. As you can see, functions are the same, input is the same, and more or less frequency for CPU is the same. But for some functions, ARM v8 simply scalarly behaves 4 times faster. So good work by ARM. So going to actual example of what I have said, we have a product that we developed following this principle. We have an ADAS solution that has 4 functions that are that should be and that are running on off-the-shelf ARM device. So we are not able to use OpenCL or any optimization that is specific to particular hardware. So we had to optimize this purely in Neon, which is generally now available almost everywhere. We design and test it using OpenCV, as I have described. We design on the desktop. We regression test then on embedded platform, but most of the accuracy tests run on the desktop because we have days and weeks of video that we have to go through each and every release, and that simply takes time. We use so-called intelligent pipeline, which I maybe can describe in a little bit more detail. So usually when you have multiple algorithms running on the same device, some of them can share results of each other, or can share results of single computation like resize and so forth. So our pipeline implements that approach. So function only executed one, computation is done once, but then all algorithm use that result, so we reduce CPU load there. We also try to minimize memory bandwidth use by combining certain functions. So as an example, we use raw camera image, we do demosaicing, white balance control, conversion to grayscale and RGB in one function that allows us to do just one memory read, more or less, so, which is very good and reduces dramatically. Few interesting things. So algorithm optimizations reduced by factor 2 or 3, and this is a number that we use ourselves only because we usually design, people that work in company usually design algorithms in efficient manner right away, so they don't use RGB images most of the time and so forth. So they try to design things efficiently right from the scratch, but sometimes it can be 10 and more. And Neon accelerations give another 3 or 4 times acceleration, not for a particular function, but for a given algorithm. So that's good to remember that optimization that is done in the algorithm can be more beneficial than actual Neon optimization. So what is missing or what is planned to make things better? First of all, OpenVX that was mentioned. OpenVX should allow you to have hardware implemented functions common CV functions, resize, and things like that in the hardware. So you could probably get very fast components of your algorithm running. And to some extent, to benefit out of this, OpenCV in version 3 will introduce OpenCV Hall, which allow you to abstract OpenCV from the hardware specifics and implement set of optimized functions in the hardware or in a very efficient manner in Neon or OpenCL or whatever. And then this should make possible for silicon vendors to deliver their proprietary optimizations separately from OpenCV as well. We also quite actively using multi-core functionality that is given by Intel TBB and by Apple and so forth. But on most of the embedded systems, Intel TBB doesn't exist or doesn't work properly. So currently OpenCV implements so-called generic multi-scheduler that is able to work with simple pthreads interface that is available on most of the platforms like QNX, for example. And I think that we are, let's say, planning or actively thinking of is to making a benchmark that could be used to evaluate the performance of the hardware. Probably we could include that in the OpenCV manager that you can download it, that you can download on your cell phone and just simply execute tests and pass the results to some website. So that functionality is not yet present and wasn't started even, but this is something that probably could be expected in coming releases. So this is just for the record. You will probably get a copy of the slides, some resources, or you can probably use a super secret site, Google, to find all this, but just to combine everything here. Okay, so.
Thank you very much, Yury. If you have questions, please raise your hand and we will get a microphone to you. While people are thinking of their question, I have a question, which is the real-time system that you implemented, did you actually run into thermal throttling issues on that? Yeah?
Yeah, I mean, constantly. And as I mentioned, there is no way to even understand that you're running into issues, except the fact that you see that performance is getting worse and something is becoming really a problem for your algorithm. So, and also, of course, you can feel that device is getting really hot.
So I suppose what you could do is build a temperature sensor and feed that back in. Never mind.
Yeah.
Other questions?
So you mentioned OpenCV HAL for, so is this something that is being done or planned to be done as defining that interface with the different hardware vendor? Is it going to use existing interfaces or?
The plan is to have some, let's say, some internals within OpenCV that will be more or less well specified. So there will be two possibilities. Either you can compile open, as we expect, so to say. Either you can compile OpenCV with the default layer of those functions, and you will get OpenCV as is. Or you can load your library and say OpenCV that it should start working with the library that is loaded. And that will make possibility to load third-party libraries that are simply implementing those functions. One of the, let's say, stopping points is that we are currently identifying list of the functions that would be needed to be included in this library. You can practically take default library and replace just few, but the important step for us is to identify the full list of those functions. good thing for this feature that maybe I should mention is that if you take like accelerated resize or something, then lots of OpenCV functions use resize. So it's not just resize that you get optimized. Lots of functions that use those resize will get speed because of the accelerated layer.
Other questions?
One of your slides seemed to indicate that one of your slides seemed to indicate that parallel processing on multiple cores was not helpful, but surely the trend is to more cores. Could you explain that a bit more?
Well, let's put it like that. I wasn't saying that it's not helpful. It is helpful, but I think that let's say multiple cores are seen as a feature that can help in 100% of the cases. I'm just saying that it's not the case. So silicon vendors are growing number of cores in the SoCs. However, they should also think of growing memory bandwidth that is connected to those chips. And algorithms like, I don't know, integral image or something like that, basically are only able to be accelerated by 4 times or something like that. And although this function is simply accumulating, it's not getting desired acceleration or on multiple cores or even on the single core because it's constantly pumping from the memory. So if you have multiple vision algorithms combined, probably you will get more benefits out of multi-core because some algorithms will be pumping from memory, pumping data from memory. Some algorithms will be locally processing. But if it is just one algorithm, then I don't think that 16 cores will be 16 times faster than one core, or like even 8 times faster in some cases. So.
Any other questions? I have one more of my own. You mentioned vision benchmarking. Can you share with us more thoughts about that or how far along you are on that?
Well, we have let's say we have our own internal set of accelerated functions, and internally right now we are using let's say a set of tests that simply execute those accelerated functions on the platform and give you some sort of score, and we execute those on customer platforms prior than we let's say commit to some numbers that we can provide to customers. So potentially we might be thinking of the possibility that we are discussing is that we could probably use that library to execute on any ARM-based device that will be provided with the OpenCV manager, and people could be just measuring scores on their devices and report that. I think probably what could be let's say generic solution is to have some sort of website or something like Geekbench where people measure stuff, but this is not even planned right now.
Got it. Thank you. All right. Well, thank you very much.